doing the right thing. You know, if we take our time and we investigate all necessary things, at the end of the day, whatever recommendation that we make from the model, okay, is actually going to see the light of the day. And that is the reason why we need to take our time. Now, the next to investigate is what we call the goodness of fit of a model. If I have what do I mean by a goodness of fit of a model? From my model, I actually get a predicted. Okay, I got a predicted Y. I want to investigate whether that is going to be a good prediction. Okay, before I use that in policy formulation, I need to first investigate whether it's a good prediction. I want to ask, how good does our model fit the data? That's why it is called goodness of fit. How fit does our model fit the data? Now, the question we're going to be asking here, do I need to model my data, the response, with covariate, or I don't even need covariate at all? There's something that we call model with covariate, model without covariate. Okay, I want to explain body mass index, and I believe I don't need any explanatory variable. That would be model without covariate. I want to explain the body mass index, and I believe I need some explanatory variables in my model. That is a model with covariate. So those are the kind of question we normally want to ask here. Okay, now I need you to pay attention. And for us to be able to investigate that, we should be ready to conduct an inference. That is why inference is coming in. Okay, so that is why inference is actually coming in. Okay, the inference that is coming in, because the way to investigate the goodness of faith will require that as you test hypothesis, it will require that I should construct a confidence interval. Let me tell you this. Statistics is like a story that goes on and on and on. You can see we don't just come to inference, we don't just come to goodness of faith. Before coming to goodness of faith, you need to first address the problem of multicollinearity, because the standard error of the coefficient, of the regression coefficient, is what we're going to use in the goodness of faith. Don't forget, in the goodness of faith, I'm actually going to make use of the standard error of the coefficient, where I want to conduct hypothesis about the regression parameter, or I want to construct a confidence interval. Please pay attention. Okay, I need you to pay attention now. If I want to compare a model with covariate with model without covariate, what do I mean? Take a look at this. Look at this hypothesis. HO is trying to tell you I don't need any covariate. Okay? It's trying to say my model, this guy here is trying to give me an impression that my model Y equal to beta naught, equal to intercept. It doesn't depend on any explanatory variable. And you can see it is only, you can see beta 1, beta 2, up to beta p equal to 0. It is only beta 0 that is not equal to 0. Okay, that hypothesis implies I want to model Y without covariate. But if you look at the alternative hypothesis, on the other hand, hypothesis on the other hand is trying to say at least one of these is not 0. At least one of that is not 0 means at least I need one covariate. That's what that means. In statistical framework, if I want to test this kind of hypothesis, where I want to test hypothesis of a model without covariate, with model with covariate, I'm actually going to use F test. Please pay attention. I'm going to use F test. Okay. Another way to call the H naught here is that the linear relationship specified is not adequate. Alternative is going to say it is adequate. This is testing significance of the overall parameters in the model. I'm going to say that again. F-test can be used to test the significance of overall parameters in the regression model. Testing model with covariate with model without covariate. If I want to do that, if I actually want to do that, if you take a look at what I have here, with the one without covariate, like when the null hypothesis is true, it means, don't forget, my y equal to beta naught, then it means my y bar, okay, if I want to get the estimate of the intercept, it is just the mean of the response. I'm going to say that again. Situation whereby I don't need covariate, it means the response variable does not depend on any covariate. Okay, y equal to beta naught plus the error. The model is just going to be y equal to beta naught. Beta naught is the intercept plus the error. Okay, it doesn't depend on any explanatory variable. If I want to estimate the intercept, then I just need the average of the response variable. Now, the F-test, if I want to decide, I need you to pay attention to equation 9. If I actually, the F-test that I'm actually going to use in testing, okay, between model without covariate and model with covariate, is actually is what I'm showing you now. What is the TSS? The TSS is actually the total sum of squared. The total sum of squared is just this guy, which is the sum of y minus y bar all squared. I'm only focusing on the deviation in the response only. That is the TSS. RSS is the residual sum of squared. And of course, residual sum of squared that I said the other time is going to be summation y, right, minus y cap predicted all squared. What is the predicted? Don't forget, this is the predicted. The model is the predicted. Does that make sense? The model is the predicted. That is what we call residual sum of squared. Residual sum of squared is unexplained variation. Why the total sum of squared, the TSS, is the total variation. Total variation. And here is the number of observation and P is the number of independent variables. And of course, when the null hypothesis is true, the distribution, the probability distribution, okay, when the null hypothesis is true, is F distribution. Has anybody heard about F distribution? F distribution, okay? When I'm conducting F test, then I need F distribution. Why do I need F distribution? I need F distribution to figure out the p-value, because I need a p-value to be able to take a decision. It's just like before a court in Minnesota can entertain a case, a court in Minnesota must have a territorial jurisdiction. If I want to conduct a t-test, I use a t-distribution. If I want to conduct an F-test, I need an F distribution. If I want to conduct a chi-square test, I need a chi-square distribution. So if somebody commits an offense in the state of Minnesota, it should be tried in the state of Minnesota because it broke Minnesota law. Does that make sense? If I use F distribution, if I use a different distribution for F-test, it is synonymous with somebody that is being tried by a court in New York, and that person did not break a New York law, even though if New York was able to establish the fact that is guilty, then whatever decision they take will be declared null and void because they do not have a territorial jurisdiction. Okay, now let me tell you this. This F is like a ratio. When the F value is small, let me tell you this. When F value is small, then it means the P value will be large. When P value is large, what is it telling you? What is telling you, you are not likely going to reject H naught. Not rejecting H naught means you do not need covariate. But situation where your F is large, when your F statistic is large, okay, then the P value will be small. When P value is small, okay, then you are likely going to reject H naught, which means rejecting this guy will mean that at least beta J is not zero. It means you need at least one covariate. That is exactly what I mean. Now, what is the takeaway from here? The takeaway from this page, we use F-test in statistical framework, okay, to test, okay, whether, to test between model without covariate and model with covariate. And model without covariate here is the simplest form of a regression model. The simplest form of a regression model is an intercept model. The simplest form of a regression model is an intercept model. Okay, now the question now is, if I have F, how am I going to compute the p-value associated with that? I think I've just explained that, with the use of R software or whatever software you have, you actually gonna have that p-value computed. And the moment you get your p-value computed, you're going to compare with the level of significance. Okay, the level of significance is the maximum probability of committing type 1 error. So situation where the p-value is less than, what do I mean by p-value in the first place? What is p-value? Okay, by p-value, I'm actually, what is the probability of observing an extreme value when the null hypothesis is true? When the H naught is true, what is the probability of observing an extreme value? Okay, in statistical testing, what we normally do is to compare our p-value with the level of significance. The level of significance is the maximum probability of committing type 1 error. So if the p-value is less than a reasonable level of significance that we put at 5%, the standard is 5%, then we're actually going to reject H naught. Now, but what of in a situation whereby I'm comparing between a simpler model and a complicated model? Then we can no longer use F-test. Instead, we use a nested F-test or partial F-test. For instance, if you look at equation 10, okay, please pay attention. Equation 10, I got x1 to sq. Equation 11, okay, we got beyond that, which means equation 10 is a simpler model. Equation 10 has covariate. Equation 11 has covariate, but there is more covariate in equation 11 compared to equation 10. This is different from situation where I do not have covariate at all. When I don't have covariate, and if I compare, model without covariate with model with covariate, of course, I'm going to use an F-test. But situation where I got some covariate in one model and I got a good number of covariate in another model in such a way that the first model is nested. It has to be nested. Let me tell you what we mean by nested. This guy, everything that you have in the simpler model must also be in the complicated model. That's what we call nested. Does that make sense? And how do we actually test between using a simpler model and a complicated model. For instance, maybe I go to New York City and uh I get into Italian restaurant in New York City. I like their food. Anytime I visit New York City, I go there. Now, let's say for instance, I actually want to look at what are the variables that determine the price. Okay, the price. Okay, and there are two variables. Maybe number one, okay, is the decoration. Okay, maybe what determine the price, maybe the decoration. Okay, decoration is one of them. And maybe I have maybe the cost of production, of producing food, or maybe rent. Okay, so if I want to compare these two models. Okay, maybe in one model I'm only looking at the effect of decoration on the price, but in another model I'm looking at the effect of decoration and another variable on it. Okay, so in that situation, I'm going to use a nested F. This is a nested F, and I need you to pay attention. Okay, this is a nested F. I need you to pay attention. You're actually going to have two residual sum of square because two modules are involved. Two modules are involved. The residual sum of square of the simpler module is this guy. Then the residual sum of square of a complicated module is the other guy. Look at that. Okay, and you're actually going to have the degree of freedom, P minus Q. You're going to have P, you're going to have Q. Okay, the Q is going to be the number of independent variables in a simpler model, and P is the number of independent variable in the complicated model. And this is also going to follow an F test, but we call it a nested F test or a partial F test. And if you take a look at this, the degree of freedom is not the same. The degree of freedom here, you can see, is P minus Q, comma, N minus P minus 1. But when you look at the other one, the degree of freedom is P, comma, N minus P minus 1. Please take notes. Okay, now this is just a mathematical framework. For instance, I want to test. Now, that is going away from there. But what if in a situation where I'm no longer testing the overall parameters in the regression model, I want to test them individually. I remember when I was working in my bachelor capsule project, when I was doing my bachelor in Nigeria. I think I work on the effect of inflation rate, exchange rate, consumer price index on the GDP. Now, if I decided that I want to test hypothesis about what is the effect of exchange rate, or what is the effect of inflation rate, or what is the effect of consumer price index, I'm actually going to use t-test for individual contribution. But when I conduct t-test severally, it has tendency to increase type 1 error. And that's exactly what I'm explaining in this page. Okay, now I'm testing the parameter associated with a particular variable to be 0 or not. Okay, now what is my alpha? Alpha for that, type 1 error for that. Every test we have its own level of significance. Okay, and if you take a look at this now, that's going to be what is the probability of rejecting H naught, given that H naught is true? When H naught is true and it is rejected, that's a type 1 error. Well, what is the probability associated with that? I want to prove to you when you conduct an individual test, okay, the probability of committing type 1 error will be inflated. That's what I want to prove. Now, and that is synonymous, the non-hypothesis is true and it is rejected, which means you know, the covariance, okay, we say it is useful, but it is not supposed to be useful. Okay, that's an error. Okay, and if we have p regressors, so many regressors, maybe we're going to compute it for each of them. Okay, when you compute it for each of them, the type 1 error will go up. Now, how do we know? Okay, because there's going to be so many numbers that we're going to compute. Take a look at that. Okay, so which means if you take a look at what I have here, we're actually going to have so many numbers of tests, individual tests, depending on the numbers of features. We're going to test when a test when beta 1 equal to 0. Okay, against when beta 1 not equal to 0, we're going to use a t-test. When beta 2 equal to 0, against when beta 2 not equal to 0, all the way to beta p. Okay, now the alpha f now, this is family-wise type 1 error. I actually want to put into consideration, the error that I'm actually going to commit conducting this individual test. And that was why I said the probability of claiming that at least one of that is not 0. When I claim that it is not 0, when it is 0, okay? So rejecting H naught. H naught is when it is 0. Rejecting H naught when it is true means you reject H naught and you declare in favor of the alternative. Now, because there are so many, I can make use of the union. Okay, I'm actually going to make use of the union. Okay, look at that. The union where J will start from 1 to P, because the union in the sense that it's either I take a wrong decision here, or take a wrong decision here, or take the wrong decision here, and that's why it's going to be union. And if you go by De Morgan's, has anybody heard about De Morgan's theorem in mathematics? De Morgan's theorem is going to talk about A union B complement equal A complement intercept B complement, stuff like that. Okay, this guy is we're gonna lead to this. Okay, which is gonna be 1 minus that. Okay, which is eventually going to be this. Now let me tell you this: when the number of independent variable is 1, if you plug in 1, what do you get? Can somebody tell me? Plug in P to be 1, what do you get? If you plug in P to be 1, what do you get? You get alpha, which means when it is only one variable, there's no problem. The type 1 error will still be preserved. But the moment P is more than 1, and maybe your level of significance that you set is 0.05, if the level of significance that you set for the test is 0.05, if you try P to be equal to 2, what has happened? What has happened? What has happened to the type 1 error rate has been inflated. Can you see that? From 0.05 to 0.0975, which means there's possibility of taking a wrong decision. Okay? And that is the reason why we need adjustments. We have different kind of adjustments in literature, Bonferroni, Torquay, and so on like that. But that is not where I'm going. Now, I said something the other time. I said that what in the multicollinearity issue, okay, because don't forget, when you conduct a t-test, okay, you're actually going to be using the standard error. This is the formula for t-test. If I want to test for individual, okay, if I want to test individual contribution, I'm actually going to make use of a t-test. What do you see in the denominator is the standard error, right? When the standard error has been inflated, okay, take a look at this. So we are tracing that problem to multicollinearity, because when the VIF is inflated, it will affect the standard error of the coefficient, and it will affect the t-test. When it affects the t-test, what is going to happen? The t-value will decrease. The t-value will be getting small. When the t-value is getting small, the p-value will be getting large. When the p-value is getting large, then you will fail to reject H naught. Even if that variable is known, is expected to be significant, it's not going to be significant. So which means we need that multicollinearity has to be taken care of. So which means one of the way, if you don't want, you know, the type 1 error to be inflated, then uh, correcting or dealing with multicollinearity is very important. Now, this is a t-test I talked about the other time. Okay, when you are testing for individual contribution, you make use of a t-test, and of course, you're actually going to use t-distribution with a degree of freedom n minus p minus 1. Okay, so far so good. Now, I think I've explained all of that. Okay, another thing that we can talk about is how do we construct the interval? This is the interval now. What am I doing? I'm constructing interval. You can see in the interval, what do you think I'm doing? What do you think I'm using? I'm using a standard error. Look at that. You see standard error? If I want to conduct an interval for the regression coefficient, okay, if the standard error has been inflated, there's going to be a wider range of the interval, and we don't and that is not appropriate at all. And let me also tell you this. um I told you the other time, one of the measure of goodness of fit, the metric of evaluation for goodness of fit, is R squared and residual sum of squared. But situation where you got so many parameters, you cannot trust your R squared, because even if you add a new variable and the variable doesn't make sense, the R squared is going to go up. And that is the reason why we need adjusted R squared. Equation 14 is a conventional R squared. Equation 15 is adjusted R squared. You need adjusted R squared in a situation where your explanative variable is at least two or more. Okay, you need adjusted R squared. Now, in addition to adjusted R squared, I mentioned the other time, if you model fitness and model complexity, situation where you got so many parameters in your model, okay, the model selection criteria is AIC, BIC, and the CP. And if you take a look at the AIC, the BIC, they are just reparameterizing residual sum of square. Do you see RSS in each of that? They are remodifying residual sum of square, because residual sum of square is only good for model fitness, but residual sum of square is not good for model or complexity. If I want to talk about criteria that are the best for model fitness and model complexity put together, is adjusted R square, AIC, BIC, and the CP. Okay, now I want to go back to our prestige example, where we're looking at the effects of education, okay, percentage of women, okay, and type on prestige. Now, the good news is, if you write the code in R, this code, LM on that, R will automatically, okay, generate result for you. I talked about the other time, individual, if I want to test, okay, take a look at it. These are the estimates, okay? These are their corresponding standard error. This is a t-value. How do I get the t-value? The estimate divided by the standard error. And this is the p-value associated with each. Okay, so you're conducting a t-test. Now, if you take a look at that guy now, okay, I need you to pay attention to this. Okay, it means initially we have a 3 levels of dummy, right? We did not use all of them. You remember the other time when we're talking about categorical predator? Okay, do not fall into dummy variable trap. When you fall into dummy variable trap, that could lead to problem of multicollinearity. Okay, here we're using 2 out of 3, and the other one is being referenced. Okay, now if I want to talk, if I want to know whether education is significant, I will look at the p-value. Okay, these are the p-value for each of that. We're comparing the p-value which is 0.05 level of significance. Now, the other time I talk about f-test, if I want to test the significance of overall parameters in the model, okay, this is the value of the f-test, and this is the p-value associated with the f-test. The p-value here is different from the p-value here. The p-value here is for the f-test when I'm comparing model without covariate with model with covariate and testing the overall significance in the model, overall significance of the parameters in the model. Okay, now answer a question. Does our model provide a good fit? What could we do to assess if including type and women are really necessary? Okay, actually, this is the annotated. Please pay attention. Like I said, this side, okay, is the p-value associated if I really want to know the significance of each predator conducting a t-test. Okay, now based on the information here, okay, what if in a situation where I ask you to obtain what is the standard error? Please pay attention. Sigma cap, like this guy, the standard deviation, the estimate of the standard deviation. Okay, there's a difference between standard error and residual standard error. Look at this. Residual standard error is sigma cap. That's a residual standard error. Residual standard error. But this guy, they are the standard error of each regression coefficient. The two of them are not the same. Pay attention. Now, when you want to talk about the R squared, this is the R squared. You say they want to multiple R squared. You multiply by 100. The R squared give how much percentage variation in the response the model was able to explain. And I said when the variable is more than is 2 or more, we talk about adjusted R squared. You see, adjusted R squared, R has automatically computed all of that. Okay, and that is exactly what I'm explaining here. Now here, this will give me an opportunity to see whether each of the predator is significant or not by conducting a t-test, look at the p-value, and it's also going to give me information about whether you know I need a model without covariate, or I need a model with covariate that we call the f-test. And of course, the p-value for that is actually here. You see the p-value here? Okay, that is the p-value for the f. Okay, when you are testing model without covariate against model with covariate. Now, what are we going to do next? Let me tell you this. Whenever there's a violation of assumption, whether assumptions of normality or assumption of constant variance, or there's an outlier, or there is a high leverage and so on like that. Okay, now we now begin to look for solution, and one of the way out is to see whether the response variable is in statistical form or not. If it is not in a good statistical form, we now begin to think of transforming the response. Does that make sense? So what I'm going to do next is we don't transform our response if there's no problem. We go into this if there's a problem. And how am I going to know if there's a problem? I'm actually going to know if there's a problem through regression diagnostics. If I don't diagnose, there's no way I'm going to know if there's a problem. I told you statistics is like a story. Okay, so what I'm going to walk you through on Wednesday is going to be on transforming response. Now, before I go, because I used to listen to feedback, initially I set meet time for this course for Friday. Okay, it's going to be the following Monday. Why? Because we have some students in this class. Okay, they are taking 5401 that I used to have before this class. And the way I put the exam before is going to be Fridays. So because of that, that would be too much for those students who are taking the two courses. And because of that, I'm going to put it on announcement section today. Okay, the exam for 4052 is not going to be that week Friday. It's going to be the following week Monday. Does that make sense? Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you, Professor.
You welcome. How are you doing?
I'm doing